Today we are going to discuss a most important concept of relativistic electrodynamics. In fact, in this lecture, we will explore the concept of electromagnetic field tensor. Actually, this electromagnetic field tensor is expressed in matrix form, in fact a 4x4 matrix. The matrix elements in fact give the components of electric field vector E and magnetic field vector B. But how? How we will get the components of E and B in terms of the electromagnetic field tensors matrix elements? This is in fact what we have to discuss in the present lecture. You should remember, and you will get after this lecture, that this electromagnetic field tensor is in fact a skew-symmetric or an anti-symmetric tensor of rank 2, and so it will have in fact 16 components in the three-dimensional Euclidean space, and those components are in fact the electric field vector and magnetic field vectors components in Euclidean space. So as our purpose is to find the components of field vectors E and B, so to explore the idea, our starting equation will be in fact the defining equation of electric field vector E and magnetic field vector B in terms of the electrodynamic potentials, which are denoted by, the symbol phi and A, and in fact they are called a scalar potential and vector potential. So in terms of these scalar and vector potential, we will define electric and magnetic field vector, and after that we will develop the idea of this very tensor, which is known as electromagnetic field tensor. So let us start to discuss this very important field tensor, that is electromagnetic field tensor, by the use of the defining equation of electric and magnetic field vector. As you know, we know that electric field vector E is defined in terms of phi and A as minus grad phi minus del A del T. This is how we define electric field vector E in terms of the scalar potential phi and vector potential A. Let us say this is equation 1. And at the same time, we also define magnetic field vector B, and it is defined as curl of vector A. This is our starting equation, and we have a aim to find the components of E and B in terms of this particular electromagnetic field tensor. Actually, you know that the electric field vector E and the magnetic field vector B are not 4 vectors, but they are in fact geometrical vectors, and so in a three-dimensional Euclidean space, E will have 3 components. Vector E has 3 components, that is, you may say x component, y component and z component. And similarly, B is also not a 4 vector, and so it has also 3 components in the 3-dimensional Euclidean space. Taking in account of the 3 components of these vectors as a whole, there will be 6 components, and taking these 6 components of these 2 vectors, we will develop the antisymmetric tensor of rank 2, and that very antisymmetric tensor of rank 2 is in fact electromagnetic field tensor. For convenience, we write the x component of electric field vector Ex by the symbol E1. Instead of Ex, we will use E1. Instead of Ey, we will use E2. Instead of Ez, we will use E3. This is for convenience, as you will see. If we use the index instead of index x, y and z, the numerical subscript 1, 2 and 3, there will be a convenience in taking the summation. Similarly, instead of Bx, what we will write? We will write B1. Instead of By, we will write B2, and instead of Bz, we will write B3. This is just for convenience. You may write even Ex, Ey, Ez, Bx, By, Bz, but for convenience we use such symbols, so that whenever summation will be taken, there will be a clear-cut concept in your brain. Either you will confused when x, y and z will be used. So, as our purpose is to find the electric and as the components of electric and magnetic field vectors, so we will write the above 2 equations, that is equation 1 and equation 2. Let us say for convenience that this is equation A and this is B of equation 1. There will be a large number of equations, so I use this particular equation number A or B. So we consider 2 equations in one, that is 1A and 1B. Now, in terms of the scalar components of vector E and B, we want to write equation 1 and 1A and equation 1B. So, write the first component of electric field vector E. In terms of scalar components, equations in 1 are written as see equation 1A, its first component, that is x component, which I will write E1, will be what? Grad phi. The first component of the vector grad phi will be what? That will be in fact del phi del x1. See here, instead of x I have written x1 and minus del a del t. So write its x component, that is del a1 del t. Let us use a simple algebra here. In fact, our aim is to express in terms of the four-dimensional geometry of these components. So I just use a simple technique. We multiply by a factor I over c in both sides of this equation. So the above equation may be written as I over c E1. I have just multiplied by the factor I over c, and so each term will be multiplied by the same factor, and so it will be minus I over c del phi del x1 minus I over c del a1 del t. And as I over c is a constant, so we may take this factor inside the operator. So you can write it as del x1 I over c phi and plus del a1 by del ICT. See here, as 1 over I is minus I, so instead of minus I have written 1 over I. C is again a constant, so you may write it inside the differential operator. So this term may be written like this. Now, as we know, when we have studied in fact the 4 vector potential, then you have seen this is what? I over c times phi is what? In fact, this is 4th component of 4 vector potential denoted by the symbol A4. So we will write A4 instead of this I over c times phi. And ICT, what is this? This is in fact 4th component of the radius vector, and it is denoted by the symbol x4. These facts already we have studied in previous lectures. So we finally get I over c E1. This equal to, let us write the second term first. This is del A1 by del x4 minus del A4 by del x1. Del x1. Say this is A. I have just found the first component, that is x component of electric field vector, in a particular fashion by multiplying it by the factor I over c in terms of the 4 vector potentials component A1 and A4. In a similar manner, we can find E2 and E3. So by induction you may directly write the equation, or you may exercise yourself by taking the same step as I have followed. So I am directly writing it in a similar manner, similarly we may write I over C E2. And what will be this? Let us see. When there is E1 here, the electrodynamic potential first component A1 is in the first term and A4 is in second term. So by taking the idea developed in A or by induction, we may write it as del A2, because here is E2, over del X4 minus del A4 over del X2, since when there is E1, here is X1. So if it is E2, here will be X2, and say it is B. Now, in the similar manner, we may write the expression for I over C E3. By induction, let us think what we have to write. You may think that this will be simply del A3 del X4 minus del A4 del X3. I have written these two equations just by induction, seeing the equation A, and say this is equation 2. Equation 2 has three parts, defined in A, B and C. In this way you see that how we have defined the three components, which are in fact X, Y and Z components of electric field vector E. Now, on the basis of second part of the equation 1, that is B equal to curl A, we will find the components of vector B. Now I am just repeating that equation. B equal to curl of A, and you know how curl of a vector is defined. In determinant form we write it, this will be simply I J K del X, here X will be written as X1, del Y, Y is written as X2, del Z, it is written as X3, and now the components of vector A, this will be AX, and instead of AX we will write A1, instead of AY we will write A2, and instead of AZ we will write A3. This is just a simple determinant. You may simplify it. What will be our result? Our result will be, see here, del A3 del X2, del A3 del X2 minus del A2 del X3 I. In second term of the determinant there is negative sign, but we take positive sign, and so the order of operation will be reversed. So what will be the term? The term will be del A3 del X1, del A3 del x1 minus del A1 del x3 j plus what will be this term? Del A2, see the determinant, del A2 del x1 minus del A1 del x2. And this is unit vector k. So what we see, in fact this is the x component of vector b, this is its y component, and this is its z component, which we denote by the symbol b1, b2 and b3. So in the light of this result we may write for vector b, what we will write? b1, which is in fact bx. b1 is equal to, let us see here, this is the value of b1, this is del A3 del x2 minus del A2 del x3. Say this is A. Again b2, which is in fact by, this is in fact by, this is b2 you may say. So this is equal to what? This is in fact del A3, b2 is del A3 by del x1 minus del A1 sorry, here we have done the mistake. Order should be reversed in this equation, so there will be plus here and minus here. I have told you that the order should be reversed, but I have not reversed the order, so the term will be like this. So in this equation, in fact this will be minus and this will be plus. Del A1 by del x3. Say it is in fact b. Now similarly b3 is what? b3 equal to del A2 by del x4 minus del A1 by del x2 del A2 del, here is also in fact this is del x1 not x4, this is del x1 this is equation C. Say this is equation number 3. So equation 3 has also 3 parts defined in A, B and C. Now we have found the components of electric field vector E and magnetic field vector B as you see in equation 2 and 3. In fact, from these two equations 2 and 3, it is clear that all these equations can be written in a particular manner. We can write it. We can write equations in 2 and 3 as. How we can write? Let us first write and then we will understand how that equation represents all those components. We write it in a particular manner. F mu nu equal to del A nu by del x mu minus del A mu by del x nu. Say it is equation 4. In fact, here mu and nu will be assigned the values 1, 2, 3 and 4, and when we will assign these values we will get the all above components. As I am just writing what this f mu nu represents. So you may write the values of f mu nu in this form. You see seriously here that here I over C E1 is what? See the above equations. In fact, this is F41. It means when you will put mu equal to 4 and nu equal to 1, you will get in fact I over C E1, as you may see in above equation. Again, I over C E2. See the above equation. This will be in fact F42. You may verify it. And I over C E3, this will be in fact F43. Similarly, from equation 3 you will get that F12, that is when mu is 1 and nu is 2, that will represent in fact B3. F23, this will represent what? This represents in fact B1. This is B1. And F31, this represents B2. One thing here is also very remarkable, that when we will interchange the index mu and nu, the value will remain same but the sign will be reverse. Just see, I can write F mu nu equal to, if we take minus sign common, the result will be what? This will be del A mu by del x nu minus del A nu by del x just I write it here minus del A nu by del x mu. See the bracketed expression. As we have written f mu nu defined in equation 4, see here, then this bracketed term will represent what? This will represent this sign, minus sign here, minus f nu mu. So we see that f mu nu is in fact equal to minus f nu. F mu nu is equal to minus f nu mu. Again, if we take the two index same, if mu equal to nu, then f mu nu will be simply written as f mu mu or f nu nu, whatever you write it. And what will be our result? The result will be, replace all the nu by mu, we will get, this will be del A mu by del x mu minus del A mu by del x mu, and so these terms will cancel out and the result is 0. So what we get? We get that finally f mu mu is equal to 0. So all those components for which these two indices will be same will be 0, and the components, whenever the indices will be just reverse, the component will change into its sign, its value will remain same. So taking these facts into your consideration, now we can write this quantity f mu nu in matrix form. So in matrix form, we may write f mu nu as, first of all I just write symbolically it, and then we will put the appropriate value which are defined in above equations. So f mu nu, this matrix will be represented by f11, f12, f13, f14. Again f21, f22, f23, F24. Again F31, F32, F33 and F34, and the fourth row will be F41, F42, F43 and F44. Now let us substitute the values of these components, these elements of matrix as we have find above. So that is, we may write F mu nu equal to, let us see, F11, we have seen above F mu is 0, so the two indices are same, so the first matrix element F11 will be 0. F12, see above, F12 is simply B3, this is B3. F13, you see above, F31 is B2, so what will be F13? By the property F mu nu equal to minus F nu mu, you may say F13 will be equal to minus F31, and so that will be equal to minus B2. So here will be minus B2. And F14, see above, F41 is I over C into E1. So F14 will be what? That will be simply negative of that value, and so that is minus I over C E1. I over C E1. Again F21, see above, F21, in fact F12 is B3, and so F21 will be minus B3. This is minus B3. Again there is F22, indices are same, so this element will be 0. F23, this see above, F23 is in fact B1, so this is B1. And F24, F24 will be equal to minus F42, and so it will be minus I over C E2. Now there is F31, see here, F31, this is simply B2, see above, B2. F32, F32 will be equal to minus F23, and so it will be minus B1, minus B1. Again F33, indices are same, so it will be 0. And F34, this is minus F43, and so it will be minus I over C E3. Now F41 is what? This is I over C E1. F42, this is what? This is I over C E2. F43, this is I over C E3. And F44, indices are same, so this element will be 0. In fact, this is the matrix defining the quantity F mu nu. There are 16 matrix elements of this quantity in which is clearly seen from equation and not 4, but this is equation 5. See equation 5. In fact, this quantity f mu nu, which have 16 component in this, now you can say the 4D space, and so this quantity is neither a scalar nor a vector, but it is a tensor of rank 2. And as we have seen, f mu nu is equal to minus f nu mu. It means it is what? It is an antisymmetric tensor. And this very tensor f mu nu is known as electromagnetic field tensor. For your convenience, I just write this statement. This tensor f mu nu is called electromagnetic field tensor. Electromagnetic field tensor. And since f mu nu is equal to minus f nu mu, and simultaneously we have f mu mu is equal to 0, so you may say that this property says that it is an antisymmetric tensor. So this implies f mu nu is an antisymmetric tensor of rank 2. It is an antisymmetric tensor of rank 2. So you seen how I have developed this antisymmetric tensor starting from the defining equation of vector E and vector B. In fact, to clarify the concept, or you may say how we can say that this tensor represents the components of electric field vector E and magnetic field vector B, I just want to illustrate it by giving two simple examples. For illustration, we take two simple examples for illustration. For illustration, in equation 4 and 5, we have defined in fact f mu nu in matrix form and in a particular equation. Taking these two equations, we will in fact show how these two equations represents the equations defined equations 2 and 3. So let us take an example. Number 1, we want to write the equation for, suppose E3. You may take E1 or E2, anything. We have considered E3. We want to write the equation for E3. Then from equation 5, it is clear that E3 corresponds corresponds to. For E3, we may see from equation 5 what will be the values of mu and nu. Let us see. Mu for E3, mu is equal to 4 and nu is equal to 3. Or you may also say for E3 mu is equal to 3 and nu is equal to 4. You may see here equation number 5. See the equation number 5 and compare with the above equation. I have to write expression for E3 in fact. So see this term containing E3, and for this term you may see that the symbol is F34, which means mu is 3 and nu is 4, and E3 is also contained in this equation, and for this term is instead of F43. So we have mu equal to 4 and nu equal to 3, and so we have taken these values of mu and nu from equation 5. So now write the expression for F43 or F34. We may write it. So equation 4 becomes equation 4. I am just for your convenience writing down the equation 4 again. What is our equation 4? This is F mu nu equal to del A nu by del x mu minus del A mu by del x nu. And see this equation. I have taken first set of mu and nu, mu equal to 4 and nu equal to 3. So from this equation what we will write? F43, and this will be what? This will be del A3 by del x4 minus del A4 by del x3. This result is obtained when we take this set of values mu equal to 4 and mu equal to 3, and if we find F34, take this values. This will be del A4 by del x3 minus del a3 by del x4. What you see in this equation? You can easily see that these equations in the light of equation 5 yields. What does it give? It in fact gives, so we may say that it gives I over C E3 equal to del A3 by del x4 minus del A4 by del x3. You see that this F4A3 is what? This is in fact I over C this much. And in fact, see the above equation, you may see that this is in fact our field equation defined in equation 2C. This is our field equation 2C. So from this example, now it has been clear to you that the equation 5 from equation 5 we can find the components defined in above equations. Now let us take another example for more clarification. In fact, we want to give an example for the component of magnetic field vector B. So we want to write the equation for B2. Let us say, you may say B1, B2 or B3, anything, B2 component. I want to write the equation for B2 component. Then for B2, you see the equation number 5. What will be the values of mu and nu? For this, from equation 5, you may see that mu equal to 1 and nu equal to 3, or the another set will be mu equal to 3 and nu equal to 1. I am not showing that matrix. You may see and verify these values. So now what our equation 4 will become? Just I have written the equation number 4 again here. See this equation. When the defined values of mu and nu will be put in this equation, what result we will get? I am just writing those results. Let us see. If we put these values of mu and nu and these values of mu and nu, what will be our result? So equation 4 becomes, what this equation will become? Let us take this value, f mu nu, mu is 1 and nu is 3. So this is F1 3, and put the indices mu and nu in RHS. This will be in fact del A3 del x1 minus del A1 del x3, or F31, and this F31 will be what? This will be del A1 by del x3 minus del A3 by del x4. No, not 4, this is in fact 1, del x1. Del x1. So what you see, both of these equations in the light of equation 5 in fact gives us what it gives. So it gives F13 or F31. In fact it defines in fact B2, and so this is B2 equal to what? Del A1 by del x3 minus del A3 by del x1. Or in fact what is this? This result is in fact the component of magnetic field defined in equation 3. This is simply B2 defined in equation 3b. You may see above equation 3b. So we have seen by these two examples how we can find the components of electric and magnetic field vector B in terms of the 4 vector potential A, mu, nu, and by using and it is found by the use of the idea developed for the electromagnetic field tensor. In fact, in similar manner we can check that the above equation which defines electromagnetic field tensor F mu nu, that equation is in fact 4. In fact, this equation correctly represents the equations for the remaining components of electric field vector E and magnetic field vector B. So in this lecture we have developed the concept of electromagnetic field tensor F mu nu, and you have seen how we can find the components of electric and magnetic field vectors in terms of these electromagnetic field tensor. In the forthcoming lecture we will find the applications or the use of this very electromagnetic field tensor, and so we will enjoy this idea in the forthcoming lecture too. And that's all. This is all for today.